Chemistry tutor. My name is Jason. I'm going to be your teacher here during this course. And what you're going to find is that during the entire DVD series where we talk about chemistry, we're going to take every single topic from step-by-step chunks, manageable chunks, and we're going to build your knowledge in small little incremental measurable steps so that every step along the way you're going to be able to follow everything that's going on. Before you know it, you'll be balancing chemical reactions and calculating the yield of a chemical reaction without any problems. Now, I will tell you that chemistry is one of the subjects that a lot of students really do have trouble with when we first begin. When we start taking chemistry, when we grow up a little bit, we take that kind of class. The reason is that almost every single problem that you are going to have in your chemistry class is going to be a word problem. So a lot of people don't like word problems. You have to read it, and more than that, you have to understand it. That's really the challenge there. The number one thing that students do wrong when they read a word problem, read a chemistry problem, is that they'll try to take the numbers in the problem and add them or subtract them or do something to them to try to get to the answer without really reading and seeing what the problem's really and truly asking you to do. And that really is the key. You have to read it, you have to understand what is being asked and what you were given so that you can outline a logical path from start to finish. And that's the kind of skill base that we're going to get when we do these problems in this class, because all of the problems that we do here are going to also be word problems to give you that practice there. Now let me jump back a little bit. Chemistry is incredibly interesting. It's one of the few branches of science that you can really study in whole and really feel like you have an everyday connection to it. And that's why I think it's so interesting. I love and enjoy physics. I have a degree in physics. It's really neat. But when you start getting into advanced physics, you really lose the ability to visualize what's happening. When you have a electric field or something in a room, it's invisible. You can't touch it. You can't taste it. You can't see it. So it's very interesting. I love that stuff. But it's not very tangible a lot of times when you get into the advanced stuff. But chemistry is something that you can open up your kitchen, open up your refrigerator, and see things that were made chemically all around you. So it's something that you come into everyday contact with, The plastic that you use when you put it in a Ziploc bag or a zippy bag or something and throw it in the freezer, some kind of food. That plastic is a long chain of atoms that are bonded together, and someone designed that chemical to be strong, to be plastic and pliable so we can move it, to be temperature resistant. It was engineered to serve a function, and they built it, they put it together, and we use it every day. Aluminum foil, that thin sheet aluminum foil, very, very useful. It's, people go in the factories, figure out how to extrude that aluminum, figure out how to make it flat so that we can use it. All the way to rocket science, the most powerful, I shouldn't say the most powerful, but one of the most powerful and energetic chemical reactions that there is if you take hydrogen gas, or liquid hydrogen, if it's liquefied, that's the same stuff, the hydrogen is the same stuff that we put in the Hindenburg years ago, unfortunately burned and went up in flames, but hydrogen, and you take oxygen, right, and you put them together, mix them together, two very simple things off the periodic table. You mix them and you ignite them, and what do you produce? Water, right? But it's a very energetic reaction. We also produce a lot of heat, and that causes those gases to go really, really fast right out the back of a rocket engine. And that's, one of the most powerful rocket fuels that we have. So we go all the way to rocket science. We can really understand how chemistry can boost a rocket into space, all the way back down to your kitchen. If you take, some baking soda right off of the shelf, and you take some ordinary vinegar right off the shelf, and you put some baking soda in the cup, you pour some vinegar right on top of it. You don't have to light it. You don't have to blow on it. You don't have to cool it. You don't have to heat it. But just the act of pouring those two things together will cause a chemical reaction to happen, to bubble up, producing a gas, and we'll talk all about that stuff a little bit later. But I guess the point I'm trying to make is that chemistry really is all around you. When you have a matchbook, you strike the tip of that match, that's a chemical that someone has designed and tested and put on the tip of that match to serve a function. Plastic, cars, rubber, it's everywhere. And a lot of students have difficulty with this class, but we're going to break down those barriers here. Now there's one final note that I'm going to tell you here as a sort of a piece of advice before we get started on this journey. And that is that even though a lot of students have problems with chemistry, there are two main reasons that we have these problems. The first reason is because the definitions, right? The definitions. That is the most important thing. We really have to make sure we know what we're talking about. So when I tell you that I'm talking about a molecule, you really think you understand what I'm talking about. Everyone has their ideas. You may have your own idea what a molecule is right now. Maybe you're correct, maybe you're not, but we have to make sure we're on the same page. Definitions are key. So that's really what this section is going to be, a lot of definitions. I'll try to make it a little interesting, but basically you have to have the terminology down. The second thing is what I talked about before. Very, very important when we read our problems, not just to kind of glance through picking out numbers. That's not what we're doing. We need to really read it and really understand it. With that, you'll know what to do. The other thing I'll say is that when you're doing chemistry problems, to be truthful, most of the time, you're just going to be adding, subtracting, multiplying, and dividing, right? I don't want to say there aren't any equations or formulas in chemistry, because there are, but when you compare chemistry to maybe physics or something, physics is chock full of equations. You have to understand the equations. Chemistry, you really don't have too many equations, but you have a ton of concepts, and we have to understand those concepts. But you're not going to get any higher in the math more than addition, subtraction, multiplication, and division most of the time. So pat yourself on the back. If you know how to add, you know how to multiply, divide, and subtract, you're in pretty good shape. But what we need to do together is build the logic. So we're going to do that here. All right, so what is chemistry? That's the number one thing we need to answer. I think most people have a pretty good idea about what chemistry is, but let's explore it together. If I had to write a definition for chemistry, and I had to keep it short and sweet, my definition is the following. It's the study of the composition and structure of matter and changes that occur in matter. Now, one thing I'll say for everyone here listening is that when I write definitions, and I try not to front load all of the lectures with definitions, but we just have to do it in this case, I'm going to generally write them down because it helps me articulate what we're saying. It forces me to read every word, and I think it forces you to read every word. So I could blast the screen here with a large definition that you have to kind of scan through, but I think there's something gained in reading every word as it goes up on the board, just like a regular classroom. So that's what we're going to do. Chemistry is, this definition pretty much should fall in line with what you probably have in your head. It's the study of the composition and structure of matter and changes that occur in matter. When we say changes that occur in matter, we're talking mostly about chemical reactions. That's mostly what we're talking about. So we're going to spend a good chunk of time in the beginning of the class talking about what is an element. How do you calculate? How do you figure out how elements join together? And then once we understand that, we're going to combine different things in a chemical reaction to form a new product. Hydrogen plus oxygen gives you water. Carbon plus oxygen gives you carbon dioxide or carbon monoxide. How does all that come together? How do we know what's going to be formed and how much of it will be formed if we put, different amounts of chemicals together? How much of the stuff is going to come out the other end? That's really what we're trying to do in chemistry. It's one of the most important things. So I'm giving you a couple of examples, but if I had to give you a couple of additional examples, what about wood when we burn it? When wood burns, right? If we take a piece of wood and we put a match to it, what happens? Well, we get a lot of smoke and we get some heat, right? That is a chemical reaction. Oxygen in the air is combining with, basically it's combining with the wood and everything else in the wood. We get carbon dioxide, and then of course the particles that we see, the smoke is just the little particles that have, after they've been burned, floating up into the sky. But we have carbon dioxide and a host of other things that come out of burning. That's a chemical reaction. What else do we have? Something maybe you may or may not have thought of as a chemical reaction. What if we take iron and we watch it rust? Well, what happens here is we have the iron reacts with the oxygen And what we get out of that is iron oxide. Now notice I'm not writing this down into a chemical reaction in terms of the elements combining and giving you a chemical formula on the end. We're going to get into all that stuff later. Right now we're just trying to build the concepts. This is an example of the stuff that we're going to really study in chemistry. You take something like iron, you just let it sit in the atmosphere. Over time, the oxygen will combine with that iron spontaneously. It's just a natural process. And out the other end, you'll get what we call iron oxide, which is rust, which is orangish, material. Almost the entire surface of Mars is iron oxide, so it's been oxidizing for a long time. But if you take a piece of iron, stick it outside, 5 months later, come back, you'll see some kind of brownish, reddish coloring on it. That's a chemical reaction. All right, and we already talked about rocket fuel. When we take hydrogen and oxygen, we combine them together, we get water. Of course, we also get heat out of it because that's a reaction that has heat involved in it also. All right, so that's just a general idea, general overview of chemistry in general, the kind of things that we're going to be looking at. Now, obviously, chemistry is a mathematical science, so we're not just going to be writing words down. We'll have elements and we'll have amounts and in terms of how much of things that we mix together and how much is produced, and that's what we're going to be interested in calculating. Now, in order to get anywhere else in our journey in chemistry, we have to follow sort of a logical sequence. Some of the stuff I'm about to tell you, you probably already know from second grade. I'm pretty sure most of you already know that everything is made of atoms. But what we need to do is start at the beginning. Maybe there's a nugget in there that you didn't quite know, but no matter what, we need to start at the beginning and make sure that you understand everything so that as we get to the end, I'll build you up so that nothing will be left out. So, if you understand what an atom is, you'll understand our first little guy right here. What we have is the concept of an atom. And for those of you who know what this is and maybe haven't revisited it in a long time, we'll just talk about it here. It's basically the smallest elemental. And by the way, there are a million definitions for an atom you could write down, but this is mine. Smallest elemental unit in a sample of matter. All right, so what are some examples of atoms? There are things that you've heard of, that you've played with, that you've touched, and even that you've breathed. What about the atom of oxygen? All right, the chemical symbol for oxygen is the letter O, right? So that is an atom. We also call it an element because I'm kind of alluding to a few things here that we'll conquer here in a little bit, but there's a periodic table of all of the elements that we know about. And those elements are basically arranged. So everything in the universe that we know about is made up of these elements, which are just different kinds of atoms. And they combine in different ways, much like hydrogen is a gas, it's explosive. Oxygen is a gas, colorless, odorless, but we breathe it, we use it, right? You take the periodic table of all of the elements that we know about, and those elements are basically arranged. So everything in the universe that we know about is made up of these elements, which are just different kinds of atoms. And they combine in different ways, much like hydrogen is a gas, it's explosive. Oxygen is a gas, colorless, odorless, but we breathe it, we use it, right? You take those two things together, they chemically react and form water. Now, water doesn't look anything like hydrogen, and water doesn't look anything like oxygen. So when you combine these things together, they form new substances whose properties are totally different from the basic things that they're made of. So that's why we have so many different things around us that look totally different. The plastic in a bag, the rubber in a tire, the glass in your house, they're all made of atoms, which are just combinations of different, or I should say they're made of different combinations of these atoms, which are these elements that we have all around us. So an example of an atom is the element oxygen, chemical symbol O. How about nitrogen? Probably heard of this. Chemical symbol is N. Our atmosphere is made of mostly nitrogen, believe it or not, and about 20% oxygen. So we have this stuff floating around, you're breathing it right now. What about carbon? The chemical symbol for that is the element C. We represent C for carbon, N for nitrogen, O for oxygen, right? Carbon is, you know, in charcoal. Carbon's in everything. It's in your body, it's in wood, anything living. Carbon, we're going to learn later, is an incredibly versatile element. It bonds in ways that other elements don't, and that's why life is really built on carbon, because it's really kind of unique and kind of cool. What about iron? We talked a little bit about iron. What would be the chemical symbol of that? You'd think the chemical symbol for iron would be I, but it's not. It's actually, if you look on your periodic table, it's Fe. And I'm kind of bringing this up because you'll see that a lot of times. Some of these elements, the chemical symbol will be the same letter as the first, or the letter as the first letter in the name, but for some of them it's going to look totally different. And that's because you have to understand a lot of the scientists who were originally doing chemistry, they worked in Latin. The original language of science was Latin, especially when you're naming things. So Fe, just as a singular example, comes from the Latin ferrous, right? So that's where it comes from. Now, if you look in your periodic table, you're going to notice a good handful that don't match the first letter here. And that's because it's some Latin root. You could probably look it up somewhere if you were curious. But you're just going to have to get used to Fe being iron. Sodium is another